In this example, we have a 10 centimeter loop, and it says here it's a circular loop. It's in a magnetic field with a magnitude of 0.05 teslas. Then we're going to ask some questions. What is the magnetic flux through the loop? What is the orientation of the loop in order to have maximum flux? And what are the maximum and minimum flux? And what is the flux if the loop is rotating? So let's start with the beginning. What is the magnetic flux through the loop? So let's write down our definition of flux. Magnetic flux is the scalar product between the magnetic field vector and the area vector. The magnitude of a scalar product is the magnitude of B times the magnitude of A times the cosine of the angle between them. A is the area of the loop, which is pi times the radius squared times cosine theta. Okay, now let's ask what we're going to put in for all of these things. B is easy, 0.05 teslas. Pi is easy. R is the radius, that's going to be 5 centimeters. Theta is the only one we're not totally sure about. We have to draw an area vector, and we have two choices. It does have to be perpendicular to the loop, so it either comes out that way or comes down this way. It doesn't matter which one we pick. Either is valid. So I'm going to draw the area vector this way. The magnetic field vector is a line that points this way. So when we do B times pi r squared times cosine theta, it means the angle between B and A. So in this case, that angle is 60 degrees because area is perpendicular to the loop. This angle is given as 30, so that one has to be 60. So our flux is 0.050 teslas times pi times the radius squared, 0.050 meters squared, times the cosine of 60 degrees. Put that through the calculator, we get 1.96 times 10 to the minus 4 teslas meters squared, or Webers. So the important thing to take away here is probably the direction of that area vector. This way is valid, this way is valid. You don't have a way to tell which area vector is the right area vector. So what you have to do is draw it and then recognize what it is you're calculating. So you're finding the flux with the area in this direction. So because it's positive, it just tells you that more lines are going in the same direction as the area vector. It tells you that the magnetic field's in the same direction, or the two components are in the same direction. Okay, what is the orientation of the loop to have maximum flux? And what is the orientation to have minimum flux? So our magnetic field lines look like this. There's B. In order to get maximum flux, we want the most lines cutting through. So if our loop looks like this, then our area vector sticks straight out. This is the orientation that will give us maximum flux. So here, your area vector is parallel to your B vector. This would also be true if our area vector stuck out the other way, if it were anti-parallel. For minimum flux, we don't want any lines to cut through the loop. So if our loop lies in the plane like this, and our area vector sticks out, then to get minimum flux, A is perpendicular to B. So here, no lines cut through, and here, most of the lines cut through. So there are orientations to get maximum and minimum flux. Part C, what are the maximum and minimum flux? Well, for maximum flux, theta is equal to 0 because they're parallel. So magnetic flux maximum equals B times pi r squared times cosine of 0 degrees. If we do that in the calculator, we get 3.93 times 10 to the minus 4 Webers. For minimum flux, our angle is 90 degrees because they're perpendicular. And our flux, oops, I wrote max, I meant min. Our minimum flux is B times pi r squared times cosine 90. Cosine of 90 is 0, so this equals 0. The last part of the question now is, what is the flux if the loop rotates with an angular speed of 100 RPM? So now we have our loop. It's not just static, this time it's moving. So for part D, let's just do another very quick sketch. There's our loop. It's in the field, and it's rotating in the field. Let's make the assumption that it's rotating about the middle, so it's just spinning like this. I think it would get weird if it was toppling another way. It might come out of the field. So we're going to assume it always stays in the field and it's rotating about the middle. Let's write down the equation for magnetic flux. Magnetic flux equals B times the area, which is pi r squared, times the cosine of the angle between the area and the magnetic field. So there's the B vector, there's the A vector, there's the angle between them. So now we have to think back to circular motion. What is theta? Theta is your angular position. Position is speed times time, so it's angular speed times time. So theta is omega times t. So what we need is a value of theta to put in here. It's going to be omega times t. We have to be a little bit careful with our units here. When we put omega t in our equation, omega needs to be in radians per second. And we're not given radians per second, so we'll have to do a conversion. So omega is given as 100 RPM. RPM means revolution per minute. A revolution is one full cycle. One full cycle or one full circle is 2 pi radians. And of course, a minute is 60 seconds. Oops, I wrote that upside down. 1 minute over 60 seconds. So when we do that in the calculator, we get omega is 10.5 radians per second. So we'll put this in our equation. We know that B times pi r squared is 3.93 times 10 to the minus 4 Webers. And that's going to be multiplied by cosine of omega times t, where omega is 10.5 radians per second. Okay, there's one example of magnetic flux done. Let's do another one. These two might be a little bit simpler, but let's get to those next. And then we'll do one that's a little bit more complicated where we have to do an integral. So for this one, let's consider two different loops. One where it has two different magnetic fields and one where the loop is bent, so they're essentially two different areas. And can we find the magnetic flux through each loop? So let's start with this guy. The net magnetic flux, so right here it's going to have a flux where the magnetic field is into the page. Right here it has a flux where the magnetic field is out of the page. So this has two contributions to the magnetic flux. So I'm going to say the flux on the left part plus the flux on the right part. The magnetic flux on the left part will be the magnetic field on the left dotted with the area on the left. Likewise for the right. So if we're going to do this, and we'll put in that B dot A is B times A times cosine theta, plus B on the right, area of the right, times cosine theta of the right. So the next thing we need to do is pick a direction for our area vector. Area has two choices. It can come out of the page or it can go into the page. Doesn't matter which we pick, it just needs to be perpendicular to the loop. I'm going to pick the area vector into the page. Okay, you would be just as right to call it out of the page. It is important though to pick the same direction on both sides, otherwise your answers won't be consistent. So that means for the left-hand part, the area and the magnetic field are in the same direction. B times A times cosine 0. And on the right-hand side, they're in exactly opposite directions. B times A times cosine 180 degrees. Okay, we can put these things in now. The magnetic field on the left is 2 teslas. The area on the left is 20 centimeters times 20 centimeters. So that's the size of that area vector. The magnetic field on the right is 1 Tesla, so the size of the magnetic field. The area on the right, 20 centimeters by 20 centimeters. And the cosine of 180 is minus 1. Do all that in the calculator. What we get for our net magnetic flux is 0.08 Webers. That our answer is positive means more of the magnetic field is aligned with the area than aligned against the area. So that's the meaning of that positive at the end. Okay, our next problem, we've got this loop, so it was a square loop and then we just bent it in half. Now we're asking, what is the magnetic flux when we send our magnetic field in at an angle of 45 degrees? Again, this loop has two parts. It's got a top part and a bottom part. So we'll call this the top part. And we'll call this one the bottom part. So our net flux is going to be the flux on the upper part plus the flux on the lower part. Our flux on the upper part is going to be B dot A, and our flux on the lower part is going to be B dot A. And then we know that B dot A is BA cosine theta, cosine theta. Okay, let's see what we're going to put in and let's see if we can find those angles. I'm going to pick my area vectors. It's going to be a little bit difficult to draw. So I'm going to say if my loop was initially upright like this, so before it got folded in half, I'm going to say that my area vector was like this. Okay, so that means when I fold it, the area vector on the top part points straight down. So the area from the top, the area for the upper part comes down. And the area for the lower part points straight out. So there's our area vectors. So this time it's the two area vectors that are different. So the magnetic field on the upper part, 0.05 Teslas. The area for the up part is 5 centimeters by 10 centimeters. Put that in meters, of course. Cosine of the angle between the area and the magnetic field. The area is down, the magnetic field is at a 45, so the angle between those two guys is 45 degrees. That's for the upper part of the loop. Now let's do the lower part of the loop. Magnetic field is the same, 0.05 Teslas. Area is the same, 5 centimeters by 10 centimeters. And angle, the magnetic field is down at 45 degrees. The area is out, so that angle is 45 degrees. Do that through the calculator, and we get a net magnetic flux of 3.54 times 10 to the minus 4 Webers. So there's the magnetic flux for that bent loop.